before we try to find the value of this integral, we're gonna make a couple distinctions. One is that an integral, as we've sort of been saying, represents an area underneath the curve, or between the curve and the x-axis. But that's not exactly what an integral does. If the function is above the x-axis, that's what the integral does. It gives you the area between it and the x-axis. But if your function is below the x-axis, an integral will come out to be negative. It'll come out to say that this is a negative area. So obviously we can't have negative area, but the value of an integral can be negative. So that's one distinction that we're going to talk a lot more about another time, but something that we want to at least briefly talk about now. And if my function goes from below the x-axis to above the x-axis, so if I was looking for like this integral, one piece of it would be negative and another piece of it would be positive, and those would sort of cancel out a little bit. So the integral itself for this one might be some small number, like, might be 1 or 2 or something small, whereas this piece might be 4 or 5, and this piece might be like -2 or -3. But we're going to worry about those distinctions a lot more later. So an integral isn't just the area underneath the curve, but that's basically what it's representing, is the area between the curve and the x-axis. Okay. Everybody good with that so far?
Yeah.
Okay. So for each one of these, we're going to sort of look at the graph, and if the function is entirely above the x-axis, we know that the answer we get will be the area underneath it. And if the function is always below the x-axis, we would know that the area between the function and the x-axis would just be the opposite of what we get for the integral. So let's start by graphing this function real quick here. So 3x is our function. Pretend I went through the origin there. Look at that, now it did. Right through the origin, 3x. And we want to know from 0 to 2, what is the area underneath this function? So the area between the function and the x-axis. Now, on this entire interval from 0 to 2, is our function above the x-axis?
Yeah.
Yeah, so maybe at 0, right? At 0, it's touching the x-axis, but between 0 and 2, it's always above. And what shape are we getting?
Triangle.
A triangle.
Yeah, it's just a triangle. So to find the value of this integral, we could go through and do the limit and the summation like we were talking about yesterday, or we could just find the area of this triangle. Finding the area of the triangle is probably much easier. But we're going to do it both ways because not every function gives you a nice triangle. So we want to see how to do it with the limit and the summation, but we also want to see if our answer in the end is correct by finding the actual area geometrically. So what is the area of this triangle? It's 1/2 the base times the height, right? What's the base of our triangle?
2.
2. And what's the height?
6.
6, right? This is 6 up here, yeah. And so what should we end up with? We should get 6, right? Our area should be 6. So in a second here, when we go through and try and evaluate this integral using calculus, using the limit and the summation, we know that our final answer should turn out to be 6. So let's see if we can do that. Hopefully from yesterday, you remember that the limit we're going to use is this, right? Every single time. And I'm going to change this c into just an x sub k, because I don't need it to be necessarily the midpoint. We're going to actually use a rectangular approximation. So this integral should be the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k. Well, what's f of x? It's just our function, right? So f of x sub k ought to be 3x sub k. times our delta x. So everybody see how that's what we had here? Limit as n approaches infinity, sum from k equals 1 to n, f of our point times delta x. Good or no?
Good.
Okay. So now all we have to do then is figure out what delta x is, figure out what x sub k is, plug them in, do the summation, and then do the limit. Sound easy enough?
Can you repeat that again?
So all we have to do is figure out what delta x is. Then we have to figure out what x sub k is. And then we plug them into this. And then we will, once we've got those plugged in, we should be able to do the summation. And once we've done the summation, we should have a new function, and we should be able to find the limit of that function.
All right, thank you.
All right. So one of the things that we talked about yesterday is that delta x is just the width of one of the rectangles. So what I'm going to do is I'm just going to draw some right rectangle approximations in here. It doesn't matter how many I draw. I happen to have drawn 5 of them, it looks like. I could have drawn 7 of them or 18 of them or 1,000,000 of them. I'm just drawing the picture just to sort of give us an idea of what's going on. And real quickly, let's think about what each of these variables within here mean. So what is the n within this limit and summation? What does n represent?
It's the number of rectangles.
Right, it's the number of rectangles or the number of subintervals. I'm going to call them subintervals, but yeah, the number of subintervals or the number of rectangles. And delta x represents the width of one rectangle, right? And 3x sub k, that's the height of the kth rectangle. So it's the arbitrary height of any rectangle that I might choose. So first off, how do we find delta x? If it's the width of one of the rectangles, which are all the same, how do I find the width of one of them?
It's 2 divided by n.
Exactly. It's the length of the entire interval, which in this case is 2. 2 minus 0, right? Divided by the number of subintervals that we have, 2 over n. So our delta x should be 2 over n. Everybody good with that? And we'll note that delta x is always 100% of the time equal to b minus a over n. Good with that or no?
Good.
All right. So if 3 times x sub k is the height of our kth rectangle, that's the height of a rectangle, and k goes from 1 to n, let's just start investigating at the first one. So when k is 1. So if k is 1, what is x sub 1? How far over do we go from the origin to go up and find our height of the rectangle?
One third.
Say that again?
Would it be like 2 over 6?
No, but we're talking about how far in the x direction do we go over?
To get to the first x, right?
To get to right here, yeah, to get to that first x value that we go up to find the height of that first rectangle.
Oh, would it be 2 over 5?
Well, okay, so I've drawn 5 rectangles, right? So it's 2/5 based on the picture that I've drawn. But how many rectangles do I have? I don't actually have 5 rectangles. I have n rectangles, right? And so based on my picture, I drew 5, but I could have drawn 6, or I could have drawn 3, or I could have drawn 1,000,000. We have n of them. So how far did I go over?
It's the biggest number over n.
It's the width of one rectangle, isn't it? Isn't that how far I went over to find the height of the first one? I went over the width of one, and then I multiplied it by 3 to find the height. Would you guys agree with that?
Yeah.
Yeah. No matter what that number is, it's always the width of one rectangle. And what is the width of one rectangle?
2 over n.
It's delta x, which is 2 over n. So what about for that's the first one. What about for the second one? What about x sub 2? X sub 2 would be right here, right? How far over have I gone now? From the-
4n.
I went over the width of 2 rectangles, right? Which is 2 over n times 2, or like you just said, 4 over n. What about x sub 3? How many rectangle widths have I gone over to get to x sub 3?
You've gone over 3.
3 of
This
them,
would
which would be
6n.
6 over n, or 2 over n times 3, right? What about x sub 4? I'll have gone over 2 over n times 4. Well, what if I've gone over k rectangles to the kth rectangle? How far have I gone over?
2kn. Oh, 2k over n.
2k over n, or 2 over n times k. So I've gone over 2 over n k times. So for the first one, when k is 1, I've gone over 2 over n times 1. For the second one, when k is 2, I've gone over 2 over n times 2. For the third one, it's 2 over n times 3. For the fourth one, 2 over n times 4. So picking any arbitrary k number of rectangles, we've gone over 2k over n. Does that make sense to everybody?
Yep.
Okay. So we now have a value for x sub k, and we have a value for delta x. So we should be able to now go in and say this is the limit as n approaches infinity of the sum from k equals 1 to n of, our function was 3x sub k, so that should be 3 times 2k over n times delta x, and our delta x was 2 over n. Good or no? Everybody okay with that or no?
Yeah.
Good.
All right. So most of the time on the AP test, this is as far as they will ask you to go when they ask you to convert it into Newton's notation for an integral. But every once in a while in a free response, they throw one out there where they want you to finish evaluating it. So we're going to practice doing that. So what do I get if I multiply all this out?
You get 12k over n squared.
All right. So yesterday we were talking about the summations a little bit, and we said that the sum of k from 1 to n was equal to what?
It's just k summed together n times.
Right, which is what? It's k is because k goes from 1 to 2 to 3 to 4 to n. Right, we're summing together all the integers 1, 2, 3, 4, 5, 6, 7 up to n. So what does that k become?
Oh, is it like the formula that we did with summing all of the numbers from like 1 to 100?
It is
then-
exactly that.
So it's n times n plus 1 over 2.
Exactly. N times n plus 1 over 2 is what the sum from k equals 1 to n of k is, right? Remember we proved that yesterday, everybody? So yes or no? Do you guys remember that from yesterday or not?
Yeah, yeah.
Yes.
Okay, well, when you don't respond, it's hard for me to know. So trying to make sure we're on the same page here. Now we can rewrite this then as the limit as n approaches infinity of the sum from k equals 1 to n of 12, and then we'll replace the k with n times n plus 1 over 2, and we still have the n squared in the denominator. Oh, sorry. I shouldn't have written this summation anymore because we did the summation part of it. So 12 times n plus 1 over 2n squared. Okay, so we did the summation for the k, and we plugged in the n times n plus 1 over 2, and now we just have this limit. Good or no?
Good.
Okay. And so how do we evaluate a limit of this function? How do we evaluate this?
We plug in infinity and look at the behavior.
Okay, so if we plug in infinity, we end up with infinity over infinity, which is indeterminate, right?
Yeah.
Okay, so we have options. One option is use L'Hopital's rule, right? Since it's infinity over infinity, we could use L'Hopital's rule. Or we might notice that this is a rational function and that the degree of the numerator is equal to the degree of the denominator. And so if we have a rational function where the degree of the numerator and the degree of the denominator are the same, then we're looking for the limit as we approach infinity. What was the simple way to do that?
You divide the coefficients.
Divide the leading coefficients, which gives us 6. Good or no?
Good.
Which is exactly what we said we should have gotten. Everybody good? All right, let's see if we can do another one. How do you think we should start this one? Graphing. All right, let's sketch a graph. Here's 4x from 1 to 4. Right, so we're going to have some rectangles in here. And we're looking for the area of this, which is now a trapezoid, right? So we should right off the bat be able to figure out what the area is, and then we can do the calculus to see if we did it right. So how do we find the area of a trapezoid? You should know that since we talked about that just the other day. should be base 1. What's the first base?
3.
Bases are on these sides, right? The parallel sides of the base.
Oh wait,
4?
sorry.
So the first base is 4, and the other base is
16.
16. Divide it by 2, multiply it by your height, which is 3. So what should we get as the value of this integral in the end? If we do it correctly, we should get
30.
30. All right. So luckily, we can do the geometry and see that it should be 30 and hope that we do it right. So every time we want to evaluate one of these using Newton's notation, we need to start it off with the limit as n approaches infinity of a sum from k equals 1 to n of f of x sub k times delta x. Good or no?
Good.
Good.
All right. What should delta x be?
Over n.
Should be what?
3 over n.
3 over n. It should always be b minus a over n. So 3 over n, right? And there's delta x. Now we need to find x sub k. So let's find x sub k by starting with finding x sub 1. So how far do we go from the origin to get to the place right here, x sub 1, where we go up to find our first height? X sub 1 should be what?
Just 3 over n, right?
Not just 3 over n. 3 over n is the width of one rectangle, right? So this piece is 3 over n. How far did we go from the origin, though? What's the x value to represent x sub 1?
Would it be 3 over n plus 1?
It should be that 1 that we had to go over to get to the start of our interval, then plus our 3 over n. So what should x sub 2 be? How far do we have to get to x sub 2? We have
6,
to go
6
over,
over n plus 1.
right, we have to go over that 1, then we have to go over 3 over n 2 times. And to get to x sub 3, we'll have to go over that 1 and then go over 3 over n 3 times. Right? So to get to x sub k, no matter what number this is, we have to go over that 1, and then we have to go over 3 over n k times. Does that make sense to everybody?
Yes.
Yeah.
So that means that when we plug this in, we should now have a limit as n approaches infinity of a sum from k equals 1 to n. And it's 4x sub k, and x sub k was 1 plus 3k over n times delta x, which was 3 over n. Good or no?
Good.
Okay. So now we'll just simplify this down. The 4 times the 3 over n is 12 over n. And if I have 12 over n times 1, that'll be 12 over n. And if I have 12 over n times 3k over n, that'll be 36k over n squared. And this time, we are looking at 2 different things within our summation. Okay? One of them is 12 over n, right? We are adding together the 12 over n's from the first one to the nth one. So how many 12 over n's do I have?
One.
No. I'm adding them from one of them to the second one, to the third one, to the fourth one, to the fifth one, to the sixth one, to the nth one.
Infinity.
Let's go back to what we were talking about yesterday. If we did this from k over 1 to, let's say, 4 of 7s, what did that equal?
28. 7 times 4.
Right, it was 7 plus 7 plus 7 plus 7, right? Or it was 7 times 4. So if I wanted to do the sum from k equals 1 to n of 7, I would do 7 plus 7 plus 7 n times, right? Or I would have, what would that be?
Seven N.
7n. So here I'm adding together 12 over n times. I have the first 12 over n plus the second 12 over n plus the third 12 over n, all the way up to n 12 over n. So what does n 12 over n's look like?
12.
Yeah, I'm going to write it as 12 over n times n to start with, but 12n over n is just 12, right? And then what about over here? These ones, I'm not just adding a constant because 36k over n squared is not a constant because of the k. With each value, k increases by 1. It goes from 1 to 2 to 3 to 4 to 5 up to n. So that should become 36 over n squared times the value of k when I sum it from 1 to n, which is the n times n plus 1 over 2. Good or no?
Good.
All right. Then we can simplify 12n over n to just 12. Plus over here, this becomes 36n squared plus 36n over 2n squared. And since this is just a limit, we can do each piece separately. What's the limit as n approaches infinity of 12?
12.
Should just be 12. And what about the limit as n approaches infinity of this rational function in which the degree of the numerator and degree of the denominator are the same?
18.
18.
Should be 18. You divide the leading coefficients, 36 over 2. And 12 and 18 is 30. Good or no?
Good.
Good.
All right. Let's try to do another one. We're going to do the integral from 0 to 3 of 2x plus 2. So let's sketch it first. Should probably make it a little steeper. From 0 to 3. It looks like this. Okay. And we're looking for that area. I'm not going to bother to find it first this time. Let's just do the integral and see if we can come up with it. So the first thing we should do is write it out as a limit as n approaches infinity of our sum from k equals 1 to n of 2x sub k plus 2 times delta x. And then we need to figure out what delta x is and what x sub k is. So what is delta x?
3 over N.
Okay. And what is x sub 1 going to be? How far do we go from the origin to get to the height of that first rectangle? Or to get to the place where we go up to find the height?
3 over n.
We go over 3 over n. And then to go to the second one, it should be 3 over n times 2. And to get to the third one, it'd be 3 over n times 3. And the fourth would be 3 over n times 4. So to get to the kth one, it should be 3 over n times k. You agree with that or no?
Do we always have to like show that step-by-step work, or is that just so you can like help us understand it conceptually?
Yeah, I'm just doing it right now to make sure you guys understand how we're getting those. If you don't write it all out, if you just write x sub k as 3k over n, I'm good with that. And in fact,
All right, thank you.
after the next one, I'm going to give you the formula to find that every time. It's a pretty straightforward formula, but I'll give you the formula to find it every time in just a second. So if we plug all this in, we get 2x sub k, so 2 times 3k over n plus 2 times delta x, which is 3 over n. And we should then be able to simplify all of that out. That should be in the parentheses there. And what does that give us? The 2 times the 3k over n is 6k over n times the 3 over n ought to be what? 18k over n squared. And then we have a 2 times the 3 over n, which is a 6 over n. Good or no?
Good.
Okay. And so now the k becomes what? N times n plus 1 over 2. And then what about the 6 over n? I'm summing together n of those. 6 over n plus 6 over n plus 6 over n times. Just means I have n 6 over n's. Good or no?
Good.
And what does that become?
Eighteen over 2 plus 6.
18 over 2 plus 6, or 9 plus 6, which is 50.
15.
Good or no? Everybody okay with that?
Yep.
All right. Let's do another one. Our limit as n approaches infinity of the sum from k equals 1 to n of 3 minus 2x sub k times delta x. And what does delta x equal?
Two over n.
2 over n. And then we need to find x sub k. So I'm going to sketch my picture again here. This one happens to be below the x-axis. So here's 2 to 4. Right. But if I do my rectangles here, doesn't really matter. To get over to the first one, how far do I have to go? I have to go over 2 units, and then I have to go over another 2 over n. And to get to the second one, I need to go over 2 units and then 2 over n twice. So what's x sub k going to be? It should be 2 plus 2 over n times k. And I'm going to give you this formula now. X sub k should always equal your a value, so how far away from the origin you are, plus k times delta x. And we'll note, if we go back to think about the other ones, here a was 0. Oops. Here a did we just lose a page? There we go. I don't know what happened there. Here, a was 0, right? And so our x sub k was 0 plus 3k over n, 0 plus k times delta x. Same back here. It was a 1 plus our delta x times k. So every time it's just been a plus k times delta x. Good or no?
Yeah, good.
All right. So now we'll plug all this in. We've got a limit as n approaches infinity of a sum from k equals 1 to n of 3 minus 2 times 2 plus 2k over n times delta x, which was 2 over n. And this gives us 3 minus 4, so it gives us -1. And it gives us minus 4k over n times our 2 over n. Which ought to give us what? A limit as n approaches infinity of our sum from k equals 1 to n of -2 over n. Right? And then this should be a minus 4k over n, right? Times the 2 over n, so minus 8 over n. Or minus 8k over n. Everybody good with that?
Wait, is the denominator n or is it
I'm sorry,
n
n squared.
squared? Okay.
Sorry about that. Good or no?
Good.
Good.
All right. And so then what should we do?
Do the summation stuff.
Do our summation. So what's our summation?
-2n over n.
Okay. And our n times n plus 1 over 2, and the n squared. And what do we end up with? -2
-2 minus 4.
minus 4 or -6. Good or no? And we'll note that this one came out to be negative, and it makes sense because, like I was saying earlier, this is all below the x-axis, so we should get a negative value. Good or no?
Good.
All right, we're going to do 2 more of these. I'll do one, and then you guys can do the last one on your own, hopefully. This one, we would not be able to check geometrically, even if we wanted to, because we've got a parabola that we're looking at. Right, 3x squared from 0 to 2. So we'll start off with our limit as n approaches infinity of our sum from k equals 1 to n. We'll have 3x sub k squared, and we'll have delta x. And what will delta x be?
Two over n.
And what will x sub k be?
UK over N.
Should just be 2k over n. Right? It's a, which is 0, plus delta x, 2 over n, times k. So this will then become, the limit as n approaches infinity of a sum from k equals 1 to n of 3 times 2k over n squared times 2 over n, which will give us a limit as n approaches infinity of a sum from k equals 1 to n of, we're going to have 3 times 4 times 2, going to be 24. Yeah. 24k squared over n cubed. Good or no?
Good.
All right. And then yesterday, we haven't done this yet today, but yesterday we talked about the summation for k squared. What is that summation?
Just from the
N
formula.
times n plus 1 times 2n plus 1 over 6.
N times n plus 1 times 2n plus 1 all over 6. Exactly. So this will now become a limit as n approaches infinity of 24 times n plus 1 times 2n plus 1 all over 6 times n cubed. And that gives us a 48n times n times n, so 48n cubed in the numerator. So the degree is the same. We just divide 48 over 6 and get 8. Good or no? Any questions on that?
If the k is squared, do you have to square the n times n plus 1 times 2n plus 1?
Nope, it's just k squared is n times n plus 1 times 2n plus 1 over 6.
Okay.
K is n times n plus 1 over 2, and then k squared is this. And there's, there's formulas for k cubed and k to the 4th and all that stuff. But the only ones you'll need to know are k and k squared.
Right, okay, thanks.
Will we ever come up with like times where the roots aren't equal, or like where we'll have like the root in the numerator is greater than the denominator and stuff?
Say that again, where the roots aren't what?
Like where the squares are equal, like let's say it's like 24n cubed over 6n squared. Like,
Where
we
the
just say
degrees
that
aren't
it's
the same?
going-
No, they'll come out to have
Yeah.
the degrees the same.
Oh, okay, like every time.
Yep, every time.
Oh,
Unless you
alright.
did something wrong.
Okay.
Any other questions? Are everybody good there? All right, last one for today. And I'll have you guys work through this one on your own. So I'll give you 5 minutes or so to work through it, and then we'll come back and make sure you guys did it right. Sound good?
Yeah. Okay.
All right, ready, go. Hopefully we started off the same way as the other ones. The limit is n approaches infinity. The sum from k equals 1 to n, 1 minus 6x sub k squared times delta x, with delta x equal to what?
1 over n.
1 over n. And with x sub k equal to what?
1 plus k over n.
1 plus k over n. Good. All right, so this should then become the limit as n approaches infinity of the sum from k equals 1 to n of 1 minus 6 times 1 plus k over n squared times 1 over n. Everybody good with it to that point?
Yep.
Yeah.
All right. So then we've got a limit as n approaches infinity of a sum from k equals 1 to n. And now we will distribute out this 1 plus k over n. So we got 1 minus 6 times 1 plus 2k over n plus k squared over n squared, all times 1 over n. Everybody good to there?
Yeah.
Okay. And then we've got same limit, same summation. As we distribute the 6 through, that's 1 minus 6 is negative 5. And if we're going to multiply that by 1 over n, that'll be negative 5 over n. And then we're going to have a negative 6 times this, so that'll be minus 12k over n squared. And then a minus 6k squared over n cubed. Does that look good to everybody? Or no?
Wait, why did you do the 1 minus 6 and then multiply everything by negative 5?
I don't think I multiplied everything by negative 5. I just did the 6 gets distributed to everything, right? Minus 6 to the 1 is a negative 6. So I have a 1 minus a 6
Oh, okay, I see.
is negative 5 times 1. And
Yeah,
then
I just-
distribute the negative 6. Okay. And so then what do I do with each of these summations? So negative 5 over n should become what?
Negative 5n over n.
So negative 5n over n. And then we had negative 12k over n squared. So the k should become n times n plus 1 over 2 n squared. And then we had minus 6 over n cubed times the k squared. So that should become minus 6 n times n plus 1 times 2n plus 1 over 6 n cubed. Everybody good with that?
Yeah.
All right, and then all of these are just rational functions, same degree on this piece, same degree on this piece, and same degree on this piece. So we end up with negative 5 minus 6, 12 over 2, and then this becomes 12 over 6, so minus 2, and we get negative 13. So hopefully that's what you all got. Any questions on that one? Or on anything we've done today at all?